Hi everyone, let me welcome you to the 21st session of ECT 204 Signals and Systems. In the last presentations you have understood the Fourier series. Today we see the continuous time Fourier transform. In one of the previous sessions I told you these tools are for which applications these tools are used. A Fourier series used for decomposing a periodic power signal, while the Fourier transform is used for decomposing a non-periodic energy signal. So let us see what is happening in Fourier transform. The contents of today's lecture are your learning outcomes, then the Fourier transform, definition of the Fourier transform of a continuous time energy signal, then the Fourier transform of a square pulse. We will compute it and we will see the impact of that, the spectrum of that and all. Then the Fourier transform of exponential signals, then the Fourier transform of symmetrical exponential pulse, and the summary of understanding. The learning outcomes are you will learn the Fourier transform for continuous time energy signal. So a Fourier transform is used for decomposing or analyzing continuous time energy signals. Fourier series used for decomposing periodic power signals. You will compute the Fourier transform of a rectangular pulse. Then you will understand the time frequency uncertainty. Then you will learn to compute the Fourier transform of exponential signals and appreciate them with the Python demos. So the Fourier transform of a continuous time energy signal xt is expressed as x of f. I use capital F for analog frequencies. X of equal to capital X of, that is equal to minus infinity to infinity xt raised to minus j 2 pi ft dt. And the inverse transform is defined. Xt can be found as an inverse as xt equal to minus infinity to infinity x of e raised to j 2 pi ft df. So this integration is in dt, so the resulting function is in capital F. Here the integration is in capital F, so the resulting function is in t. Here the kernel is e raised to minus j 2 pi ft, and here it is a conjugate one, e raised to plus j 2 pi ft. So this is how I define the Fourier transform xf, and this is how I compute the inverse transform. So x of x minus infinity to infinity xt e raised to minus j 2 pi ft dt. Now let us compute the Fourier transform of a square pulse. This has a height of a or amplitude of a and a width of t that is symmetrically placed from minus t by 2 to t by 2. Everywhere else is 0. So if you look closely into this function, you can see that the energy in the signal is completely localized from minus t by 2 to t by 2. Everywhere else the energy is 0. So this is an extremely localized function in time. So let us compute the Fourier transform of and let us appreciate that. So the Fourier transform for this pulse is needs a correction, I think. The Fourier transform for the pulse is x of, that is minus infinity to infinity xt raised to minus j 2 pi ft dt. So this function xt exists for minus t by 2 to t by 2. Everywhere else is 0. So it exists from minus t by 2 to t by 2 only. So the integral is modified, or the limits are modified from minus t by 2 to t by 2. And the value of xt within this interval minus t by 2 to t by 2 is a. So a e raised to minus j 2 pi ft dt. So this becomes a times minus t by 2 to t by 2 e raised to minus j 2 pi ft dt. So when I perform this integration, this becomes e raised to minus j 2 pi ft by minus j 2 pi f. The limits are from minus t by 2 to t by 2. So when I apply the limit t equal to t by 2, the upper limit becomes e raised to j pi ft. Okay, because there is a negative sign here. So this is a by j 2 pi f. So these limits are interchanged because there is a negative sign. So the upper limit becomes e raised to j pi ft. And the lower limit, lower value becomes e raised to minus j pi ft. So what is e raised to j theta minus e raised to minus j theta? It is 2j sine theta. So you get a by 2j pi f into 2j sine pi ft. So this 2j is cancelled. So this becomes a by pi f. A by pi f sine pi ft. If I multiply and divide by t, this becomes at sine pi ft by pi ft. So this is a special function that is of the form sine pi theta by pi theta. So if I multiply and divide by capital T, it becomes 80 sine pi f t by pi f t. This sine pi f t by pi f t is a sinc function. Okay, this of the form sine pi theta by pi theta, that's a sinc theta. So this becomes 80 sinc capital Ft. This is not small ft, it is 80 sinc Ft. So this function, when I plot in time, this 80 sinc Ft appears like this. Okay, the maximum value here at t equal to at f equal to 0, this is 80 sinc Ft plotted against capital F. So here the maximum value is 80, and this becomes 0 at 1 by t, 2 by t, 3 by t, then minus 1 by t, minus 2 by t, minus 3 by t, etc. So it is 0. There are zeros for every minus n by t. Observe that the energy in the frequency domain, you can see that this energy, the energy is distributed over all frequencies from minus infinity to plus infinity. You can see that in the time domain, the signal energy was confined within the time minus t by 2 to t by 2. It was highly localized. Energy was highly localized in the time domain. But if you look in the frequency domain, you can see that the energy is completely distributed over all frequencies from minus infinity to plus infinity. The spectrum is available for every f. Now, but you can see that much of the energy is distributed in the first few side lobes. You can see that this f equal to 0 is a DC value. It is very prominent. You can see that that signal, that pulse has a strong DC component. So the value at t equal to f equal to 0, that is a DC value. It is 80. It's a very strong component. But much of the energy is distributed in the first few side bands. Okay. Here, this is a main lobe. These are the this is a first side lobe. This is a second side lobe. So you can see that the energy is distributed. Much of the energy is concentrated around the first few side lobes. Now, the smaller the value of t, that is more localized in time, the more distributed is the energy in the frequency domain. Okay, this is a time frequency uncertainty. That is, if you are localizing the energy in the time domain, then the energy will be distributed in the frequency domain. This is called time frequency uncertainty. This is a consequence of the Heisenberg's uncertainty principle. So what this in practice says is that you can know how many frequencies, what frequencies are available in a signal. Okay, like I may be sure that say the 300 hertz and 400 hertz or 500 hertz is available in a signal, but I cannot know with precision at what time the 300 hertz or 400 hertz or 500 hertz is occurring. Okay, the more sure I am about the frequency content, the less sure I am about the where in the time scale it is occurring. Okay, this is the time frequency uncertainty. Now let us consider an exponentially decaying signal. This is xt is e raised to minus 80 ut. This is an exponentially decaying energy signal. So the Fourier transform will be x of f, that is minus infinity to infinity xt e raised to minus j 2 pi ft dt. So this due to the presence of this ut, the integral modifies from 0 to infinity e raised to minus 80 e raised to minus j 2 pi ft dt. So upon combining these two terms, it becomes e raised to minus of a plus j 2 pi ft dt. So on integration, it becomes e raised to minus of a plus j 2 pi f of t divided by minus of a plus j 2 pi f from 0 to infinity. Now the upper limit will be 0 because it's an e raised to minus infinity term. The lower limit will be e raised to 0 by a plus, that is a 1 by a plus j 2 pi f. So if I multiply and divide by the conjugate of this, it becomes it becomes a minus j 2 pi f by a square plus 4 pi square f square, or rather magnitude of the spectrum will be 1 by root of a square plus 4 pi square f square, and the phase angle is minus tan inverse 2 pi f by a, minus tan inverse or minus arc tan 2 pi f by a. Okay. So your Fourier transform has a magnitude, this absolute magnitude, and a phase angle. So this shows variation of the signal. So we will demonstrate with Python. I have a code here called XP1. So here the frequencies I have taken from minus 10 to 10 with increment 0.1, and A I have taken as 0.9, and the magnitude will be A square plus 4 pi square F square divided by 1 by that, or raised to minus 1. So 1 by A square plus 4 pi square F square, and the phase angle is minus tan inverse 2 pi F by A. And I plot this magnitude and phase against frequency as two subplots. Now then I run this code. Now you can see how the magnitude of the Fourier transform is changing. So this is the frequency minus 10 to 10, and you can see how the the magnitude of the Fourier transform varies, and this is how the angle changes. It is 1.5 for negative frequencies. It is 1.5 exactly. This is actually 1.54. That is pi by 2, right? This is a plus pi by 2, and here at frequency f equal to 0, it is a 0, angle is a 0, and here it goes to minus 1.54. Okay, so the frequency changes from plus pi by 2 to minus pi by 2. Let us go back to the presentation. Now let us consider a symmetrical exponential pulse, that is of the form xt equal to e raised to minus alpha mod t. It is e raised to alpha t for t less than 0 and e raised to minus alpha t for t greater than 0. So the Fourier transform of this is x of f, that is minus infinity to infinity xt e raised to minus j 2 pi ft dt. So this is from minus infinity to 0. This function is e raised to plus alpha t multiplied by e raised to minus j 2 pi ft dt, plus 0 to infinity e raised to minus alpha t e raised to minus j 2 pi ft dt. So this is a discontinuous function, so I have to put it into two integrals. So here this integral is e raised to alpha minus j 2 pi ft dt divided by alpha minus j 2 pi f. Okay, this is of the form e raised to ax, e raised to ax by a. So e raised to alpha minus j 2 pi ft divided by alpha minus j 2 pi f. Limits are from minus infinity to 0. And this is minus e raised to minus of alpha plus j 2 pi ft. So this is e raised to minus of alpha plus j 2 pi ft divided by minus of alpha plus j 2 pi f. Okay. So upon the lower limit will make this 0, this value 0, upper limit will be 1 by alpha minus j 2 pi f. Here the upper limit will make it 0, and the lower limit with an added negative sign, it will become 1 by alpha plus j 2 pi f. So when I add these together, it becomes in the numerator it is alpha square plus 4 pi square f square upon alpha plus j 2 pi f plus alpha minus j 2 pi f. So it becomes 2 alpha by alpha square plus 4 pi square f square. Now we can appreciate that spectrum also. So here also I have taken the frequencies from minus 10 to 10 with an increment 0.1. A is 10, so its magnitude is 2a by a square plus 4 pi square f square. Okay, and f is magnitude is plotted against f. So if I run this code is exp2. If I run this code here, this is the shape of the Fourier transform. Okay, this is the shape of the Fourier transform. Coming to the end, what you learned in this session are you understood the Fourier transform for energy signal. You saw the definition of xf and the inverse equation for xt. Then you computed the Fourier transform for a rectangular pulse and understood its frequency domain representation. Then you understood the time frequency uncertainty. Then you learned to compute the Fourier transforms of exponential signals and appreciated them. And that is the end of this presentation. I thank you all.